Hello, today we're going to study the process of an air conditioning system. This system would be similar to the one you would find in your home or in an office situation. We're going to follow the same process that you would have studied for power systems when you took thermodynamics, except that we're going to reverse the process. So to get started, I'd like to look at a schematic diagram of an air conditioning system. So over here, I have a schematic of an air conditioning system. We label the points. We have 1, 2, 3, and 4. Okay, in an air conditioning system, we have a compressor, which you'll see right here. The fluid leaves the compressor as a gas and goes into the condenser, where the gas is condensed into a liquid. It leaves the condenser as a liquid, and then it goes through what's called an expansion valve, or it could be a capillary tube. Either type of throttling device can be used. In the lab, we're going to use an expansion valve, but you can also see a capillary tube in the apparatus. You've probably seen a capillary tube in your refrigeration system in your home. If you look behind the refrigerator and you get down in the back, you can usually see these coils. Okay, it comes out of the expansion valve as a mixed flow, and in other words, we don't know the quality. It's a mixture of gas and liquid, and then from there it goes into the evaporator. In the evaporator, it goes from this mixed flow back into a gas, where it leaves the evaporator and the cycle is repeated. Okay, in order to accomplish the air conditioning, okay, first of all, as it leaves the compressor, it leaves the gas. It's at a very high temperature, higher than the ambient temperature. The condenser would be found outside. If you're, for example, for a home air condition, the condenser is what you would find outside. You probably put your hand above the condenser and you feel hot air coming out. Well, what's happening is that we take the ambient air from outside and we blow it with a fan across the condenser, and so we pull heat out of the working fluid and dump it out into the atmosphere. So that hot air you feel coming out of your air conditioning system is what's been pulled out of the working fluid. Okay, it leaves there as a liquid. It's down to probably close to room temperature now. After it goes through the expansion valve, it comes out as a very, very cold working fluid, and it goes inside of your house, and it goes to the evaporator. The evaporator would be inside. So you have this cold fluid passing, which is colder than the air inside of your house. So the air passes over the working fluid. It pulls heat out of the ambient air in your house. It transfers it to the working fluid, causing it to evaporate, and it comes back out as a gas. Now notice I've labeled the different points 1, 2, 3, and 4. We're going to use that now we're going to look at a TS diagram, which you may recall from thermodynamics. Okay, here's our TS diagram. Hopefully you remember some of this from thermo, but this line here is what we call the vapor dome. So for example, to the right of this thick line right here, we have a vapor over here. Under the dome, we have a mixed flow of gas and liquid, and then over here to the left, we have a liquid. Okay, so I've numbered this. These numbers correspond to what I showed you on the diagram just a second ago. Now, the best cycle we could possibly have is what's called a Carnot cycle. Carnot cycle does not actually exist. It's impossible to get in nature, but it would be the most efficient one if we could get it. The Carnot cycle takes place entirely under the vapor dome. So it would be this 1', 2', 3', 4'. And what we would start with is this is the compression process from 1' to 2'. So in a Carnot cycle, it's an isentropic compression. We have entropy down here, temperature over here. So we do an isentropic compression. And what you may remember from thermo is, you see this line here? These lines to the right of the vapor dome, those are lines of constant pressure. Under the vapor dome, a line of constant pressure is just this horizontal line right here. So as we increase the temperature isentropically, we're also increasing the pressure. Okay, here at 2, we're leaving the compressor, and now we're going to have a constant pressure process where we go from the gas through the condenser to a liquid. In the Carnot process, we have an expansion process where we isentropically drop the pressure down here to 4 prime, and then we go across the evaporator back to 1 prime. Okay, now in practice, it's just about impossible to accomplish anything that looks like this, because this compression process from 1 to 2 prime is a 2-phase process. Well, in actuality, it's very, very difficult to accomplish a compression process and maintain equilibrium between the gas and the liquid process. So what we do for the ideal, what we call the ideal refrigeration cycle or air conditioning cycle, is we move over here to point 1. Point 1 is a saturated vapor. So now when the gas enters the compressor only has to compress a gas. We do an isentropic compression up to 2. Then as we go through the condenser, it's a constant pressure process. And remember, this line over here to the right of the vapor dome, that is a constant pressure line. So we follow the lines of constant pressure down until we hit the saturation point. Then at constant pressure, we go across till we completely condense the mixture so that we have a saturated liquid. Now notice in the ideal cycle, we go down here to 4. We don't go to 4 prime. The reason we don't do that is because over here in this 2-phase region, it's mostly a liquid. And so if you calculate the work that you can get out of this in order that you would have to do to get, you could get work out of this isentropically, but the work would be very, very small, and in fact, the cost of the apparatus to get that work is not at all practical. So instead of putting a turbine in there to extract the work and come down isentropically, we put our throttling valve or our capillary valve, and we come down slightly not isentropically, but we come down here to point 4. Okay. So this point 4 is after we leave the expansion valve. It's not an isentropic process. However, it's an adiabatic process. So since it's adiabatic, we don't lose any enthalpy across the throttling process. So this is actually an isenthalpic process. Then we go through the evaporator, constant pressure process again, and we go all the way back over here to 1. So this process from 1 to 2, 2 prime, 3 to 4, to 1, back to 1 is what we call the ideal cycle. Okay. Now I want to show you a PV diagram. Let me get that out here. Because you're asked to do this in your report. You're asked to create a PV diagram. The PV diagram for the system that we just discussed looks like this. So over here on the vertical axis we have pressure. Down here we have the specific volume. And in this case, we start here at 1. And you remember 1 is where we go into the compressor. We do an isentropic compression. So you can see that the pressure is increasing from here up to here. So we do an isentropic compression. Then we follow that line of constant pressure. Well, in this case, we just have to go horizontally across here. And then we drop ice in tropically, well, in the Carnot cycle, we drop down isentropically to 4, and then we do a constant pressure process back to 1. Okay, the next cycle I want to discuss is what's called the actual cycle. Okay, the schematic diagram for the actual cycle looks just like the ideal cycle, but we've added a few new numbers here. Okay, so 1 is just prior to the compressor, 2 is just downstream of the compressor, but you'll see that we've added 3 here, just to the right of the condenser. We go through the condenser, come out at 4, then we drop down here to 5 before we get to the expansion valve, 5 to 6 across the expansion valve, 6 to 7 just as through the pipe, across the evaporator, and back to 1. Okay, what's going on here? Okay, well in practice, In the ideal cycle, we would be right here on the saturation line. But in practice, usually the vapor coming out of the evaporator is slightly superheated. So we're actually starting up here. It actually comes out superheated here at 8. Now, as it makes its way across through the tubing from 8 to 1, because of losses in the pipe, we've studied that, we lose a little bit of pressure. So we go from this line of constant pressure, so it's not a constant pressure process. We lose a little bit of pressure and we drop down here to 1, which you can see over here if I move the pin. Okay. Then in the actual process, we go through the compressor. Well, for the ideal process, we said the compressor was isentropic. Well, in reality, there are some irreversibilities, and it's not necessarily adiabatic. We could either go up here to 2' as we shift to the right, or we could go to the left, depending on whether heat is absorbed or released. It depends on the ambient conditions. So we could go in either direction. So anyway, we end up here at 2, which is over here. From 2 to 3, we're just going through pipe. Okay? We're going to lose a little bit of pressure, so we're going to drop from this line of pressure down a little bit to this line of pressure, or maybe further. Okay, then we hit the vapor dome, and we're going to go constant pressure across the vapor dome. We could actually lose a little pressure in there also. We may or may not lose pressure. Okay, so that's not necessarily a line of constant pressure anymore. And then when we come out of the condenser, we're actually going to probably be a little bit supercooled. Instead of being a saturated liquid, it's going to be a supercooled liquid, so we follow the line of constant pressure down here to 4. As we go through the pipe, we're going to lose a little bit of pressure, so we have to drop down here to 5. Then we go across the expansion valve to 6. You can see 6 to 7, we're just going through pipe, so we'll lose a little bit of pressure there. And then as we go through the evaporator, we could lose a little bit of pressure. And then we come out, and we come back up to 8 and start the process all over again. So that's the actual air conditioning cycle. Okay. Now I want to talk a little bit about how we measure performance in a refrigeration cycle, so I'm going to go to the board. The first parameter we use for measuring the performance of an air conditioning cycle is what's called the coefficient of performance, and we use the symbol beta to indicate coefficient of performance. Beta, or coefficient of performance, is just the heat removed from the air that we're trying to cool divided by the work that we have to put in to accomplish it. So Q low would be the heat that we remove from the ambient air. So that would be, let me see, that would be process 4 to 1' here. So we find the difference in enthalpy between 4 and 1. Q low, like I just said, is the heat removed from the ambient air. That is, it's the heat removed from the air in the room we're trying to cool. Okay, WC, that's the work of the compressor. That's the work that we have to do to accomplish the cooling. So the work, what we're paying for, or let's go over here. QL is what we get. That's the heat that we've extracted. We were trying to extract heat from the ambient air in the room. So that's our QL. WC is the cost. That's what we're paying for to operate that compressor. Okay, another parameter that we use to measure the performance of an air conditioning system is what's called the energy efficiency ratio. And you'll usually see this on an air conditioning system. Actually, you'll see this more often than you see the coefficient of the performance. The energy efficiency ratio is measured exactly the same way we do the coefficient of performance, except the units are different. For the coefficient of performance, that's a unitless parameter because we had energy over energy. Well, here we have the same thing, QL over WC, but in the industry, QL is specified in BTUs per hour, and work is specified in watts. Okay, so even though we calculate it the same way, we have to leave this in BTUs per hour divided by watts. So you get some number that's let's say it's 5. It'd be 5 BTUs per hour per watt. It's traditional to drop the units, though. When we specify an EER, you usually won't see units, and everybody knows that it's BTUs per hour per watt. Okay, next, how do you find Q low and work of the compressor? Okay, well, Q low is just going to be H1 minus H4. So you're going to, in the lab, you're going to be measuring temperature and pressure at the different points. You'll measure temperature, pressure at 1, temperature and pressure at 0.4, and then you can use your CAT2 software to look up what the enthalpy is at each one of these points. And the difference between those two is going to be your Q low. To get the work of the compressor, we do the same thing. We take the temperature and pressure that we get in the lab at 2. We use the CAT2 software to look up H, and then we do the same thing at 1. So that's how you do that. Okay, we also have a watt meter in the lab that you can use to compare your measurement here that you get by taking the difference in the enthalpy and compare that with what you get off of the watt meter. And you'll find they're not they're not the same. Okay, let's move on now to the report requirements. Okay, and these are all laid out pretty well in the write-up. Okay, first of all, as usual, page 1 is a letter. And all the specifications for the letter are in the write-up. Okay, page 2, we ask you to create a pH diagram. Page 2, the one on page 2 is for the low fan setting. You're going to do the experiment at a low, where we have 2 fan settings, and we'll describe that in the lab part in just a minute. But you're going to do it at 2 fan settings, a low fan and a high fan. So the first, page 2 is the pH diagram for the low fan setting. And I also want you to just find some points so that you can put the vapor dome on the diagram. I have an example down here. So these points right here are the points that you get in lab. Those are your data points. But I want you to use the CAT2 software, get some points for the vapor dome so you can see where they lie in relation to the vapor dome. Okay, so this line here is not something that you get from lab, it's something you get from the CAT2 software. Okay, page 3, you're going to create a TS diagram for the low fan setting. So your data will look something like this line. You'll have this line, this line, this, and over here. Okay, I also want you to include some data so that you can construct the vapor dome. Okay, now we'll move over here to page 4. Page 4, we just shift over to the high fan setting. So you create a pH diagram for the high fan. Page 5 is create a TS diagram for the high fan. Page 6 is your opportunity to write a discussion of what you observe. So part of your discussion, of course, will be in the letter, but you can also, there's a page here for additional discussion, and it's described in the lab write-up. Okay, page 7, and we haven't talked about this, but it asks you to calculate the volumetric efficiency and volumetric flow rate. Okay, the formula is in the lab write-up. It's pretty straightforward, so I won't go over it here. Just follow that explanation in the lab write-up, and you'll get the volumetric efficiency and volumetric flow rate. Okay, on page 8, I want you to present your coefficients of performances and energy efficiency ratios. Okay, you might make a little table or something like that, just some nice way to present the data. And I want you to base your calculations on the pressures at the condenser and the evaporator. Okay, you're going to find out that if you try to, because there's some uncertainty in the temperature and pressure measurements, you're going to have to pick either the temperature or the pressure to look up the values. Okay, so you can't do both. So I'd like you to just take the pressures. One's not necessarily better than the other, but just so we're all uniform, we'll just base it on the pressures, and you can look up the values from that. Okay, then on page 9, and you'll see what I'm talking about when you get here. It may not make sense now, but when you actually go to do this, you'll see that you need to pick either the temperature or pressure to base it on. Okay, page 9 includes your experimental data. Put it in a nice format that we can easily understand. And then page 10 will be your sample calculations. Okay, now we're going to move on and show you the lab demonstration. Thank you.
Hi, I'm Kyle. I'm going to introduce you to the AC refrigeration unit experiment. This is the equipment here. It's comprised of the compressor, the condenser, the expansion valve, and the evaporator. You'll see as you run it, it may take 20 to 25 minutes to start up. We've had this running previously, so it's almost at steady state. The first thing you want to do, if the water is not already running, is turn on the water valve. You'll be able to hear it. You may not see a flow. However, you can check these two flow meters, as this is the flow meter of the water running through these condenser coils, and the flow meter for the water running through the evaporator coils. You turn this on, you'll hear the water flowing, and you can now turn on the valves here to open up the line for the refrigerant. This is marked in the lab write-up. Make sure you turn the correct two valves. The other ones may vent coolant out into atmosphere. Once those are turned on, you can switch your main unit on with this switch down here. Now to view the refrigerant level may be a little difficult to see, but it's right here. You can turn the dial to get the piston to rise to the flow meter settings as described in the write-up. Same goes for the water for each one. You're going to adjust these twice to get the values you need and let it reach steady state. You'll see the temperature readout for all 8 sensors by turning this dial. Make sure you give it a few seconds between turning and that temperature has steadied out. That's how you'll know it's reading the correct thermometer and that you're at a steady state. And your power being used by the compressor reads out right here in watts. You want to measure all of this before or during the lab once it's reached a steady state, and then following the directions adjust the level and wait another 15 or 20 minutes for it to reach that state before taking these measurements again.